Okay. So, as Andy explained, I was asked at the last minute to give a review on surveys, so I will try to tell you what I know about all the various surveys going on, but this is necessarily going to be quite biased, and it will certainly be, at the very least, biased in a different way than what Yannick would have presented. Okay, that's the way it is. I'll try to keep it fairly general as well, and so I'll start with reminding us what are the science goals for these weak lensing surveys, why it is that there are so many of these projects, taking considerable investments of people's time and effort on the rails at the moment. So the idea, of course, for all these weak lensing surveys is to make projected mass measurements using the gravitational lensing technique. And the reason why that's interesting is that it allows you to measure a whole bunch of things about our cosmological model. In particular, the statistics of the large-scale structure, properties of dark halos. Lensing is, of course, sensitive to all the matter, not just the baryons. We saw this morning a lot of stuff on clusters. You can make detailed mass maps of clusters and compare them to simulations. And of course, what's turning into the holy grail for this whole subject is to be able to do this in 3 dimensions and to follow the growth of structure and the expansion of the universe through tomographic techniques, and that way learn something about the dark energy and the dark matter. And it looks like these are really the only ways that some of this information can be accessible to astronomical observations. So that's really what's driving a lot of interest in the field, also from outside the traditional astronomy, of course. Okay, so those are the science goals, and those translate into requirements on your surveys. Of course, the main thing we're fighting against is shape noise, the fact that galaxies are very poor tracers of the gravitational tidal lensing field because they have a very wide variety of intrinsic shapes. So you need to average over many galaxies to pull out the weak lensing signal, and that means you need to cover a very wide field to sufficient depth to get enough galaxies per square arc minute on the sky to get the resolution in your mass maps that you need. That in turn also requires good image quality. You need to be able to measure the shapes with great confidence. You need to sample your images adequately and so on. And you have to understand your experiment, and that in particular means you have to understand the blurring function that's introduced by the telescope, by the detector, by the camera, and by the atmosphere. So well understood point spread function is what people in this field actually spend a huge amount of their time talking about, as we saw yesterday already. So there's a lot of work in terms of algorithms trying to figure out the best ways to analyze these data. So this is a not to be underestimated part of any survey project. That's on the lensing side. To do the tomography, you also need to have the photometric, you need the redshift information, and so that usually for the gigantic samples people are considering means photometric redshifts, photosets, which means you need good photometric accuracy to pull that out. And again, that is a bit of a black art how you do that to the very stringent requirements that are needed to pull out the science. And even if you weren't interested in this whole tomography idea, even then you need to have, it helps a lot to have good redshifts, because you have to filter out the non-gravitational lensing parts of the ellipticity correlations that we see on the sky. Again, as we saw in some talks this morning. So there's been a lot of development in the last decade, let's say, on building ever wider field cameras. Nick showed this plot here in his talk, the growth of pixels as a function of time from 1970 to soon, and it just is completely exploding, and the amount of glass in telescope mirrors really hasn't kept up at all. So larger and larger detector arrays are certainly in. Here's a few examples. This is the Pan-STARRS camera, this is Megacam, and this is OmegaCam that we built for the VST. But there's many more projects here, and this is a roughly chronological order of many of these projects that are ongoing at the moment. It's not restricted to the optical, also in the infrared we now have very wide field imaging cameras of sizes that would have impressed people working in the optical not so long ago, and in particular Vista and Newkirk have some of the biggest cameras, which are also used for these kinds of things. They're not at the moment used for direct weak lensing measurements, because they still tend to have too large a pixel for that, and the seeing in the infrared is often a bit better. But nonetheless, they're a very important part of supporting the photometric part of these surveys. So image quality is very important. That means not only that you need small pixels on your CCDs to be able to sample everything properly, but also that you need to form good images onto your detectors. So the first thing to do is to go to good seeing sites, have telescopes which are able to take advantage of the seeing, do sensible things when you're scheduling things so that you're making weak lensing measurements when the seeing is good. And then there's many technical things you can do in your experiment to enhance the image quality as much as possible. And obvious things are correcting for atmospheric dispersion, designing your focal plane in such a way that the point spread function is as uniform and as round as you can make it. Worry about chromatic effects in your point spread function, in your optical design. And you can do many things to keep the telescope focused, so active focusing, charge shuffling like in pan-stars, or active optics to always keep your optical system as aligned as possible. And so having this well understood point spread function is a very important part, because we measure the point spread function wherever there is a star in the image that's sufficiently bright. But of course that's by definition not where the galaxies are that you're measuring the shape of, so you have to be able to interpolate in between and get the point spread function at the position of your sources that you're using for lensing. And so people are moving from the traditional approach where you take an image and you take it as given and try to figure out what was the point spread function in this image, how can I best interpolate, to trying to really understand the optics of your system and make a well-informed model of your whole optical transfer function, if you like, of your image quality, and use that as input for your weak lensing measurement. And so there's a nice paper by Jarvis et al. A couple of years ago where they go in detail through the various optical effects that you get from small misalignments that you typically have in any wide field imaging system. And how you can use simple components like that are driven by what you know about your optical system to try to make a good model for the image quality over the entire field of view, and then fit that with a relatively few number of parameters in a physical way to the stars that you have in your image, and therefore really model your point spread function as well as possible. So this understanding the optics of the system to be able to interpolate properly is a very important ingredient of this. There's many algorithms for doing weak lensing measurements themselves. We had a lot of talk about that yesterday, and I'm going to skip it for today. I'll spend a little bit more time on photometry. Peter Kapak gave a nice talk about this, but I'd like to make a few points here as well. Main point for me, certainly, is that I'm coming more and more to the conclusion that wide field photometry is I didn't write black on the slide, but I think it's a black art. It's very much non-trivial thing to do if you want to do it accurately. And even to the accuracies that you need to get good cosmology from these surveys. It's very hard work. And there's a number of effects which you really cannot avoid in wide field cameras. There's, for example, filter responses will be non-uniform over such. I mean, these filters are a square foot typically, and you cannot make them completely uniform. Particularly when you have interference filters where in different parts of the field the beam enters the filter at a different angle, you will see wavelength shifts simply from the physics of how interference filters work. In most of these systems you will get some sort of extra reflections because you have many optical elements that will give you ghosts and flat field contamination. So even when you think you take a flat field, that flat field has reflections in it which you have to correct. Even your calibration data is hard to get accurately. And then even if you can do all this calibration properly, then nonetheless you end up with taking different images of the sky and different filters and different seeing, and you have to combine those in some way to get good colors, good accurate colors and accurate photometric redshifts from your galaxies. And then of course there's the algorithmic side of how do you get accurate photometric redshifts from good photometry. So here's one example. This is from the design of Omega Cam, our VST camera. This is the end of the optical train. These are two lenses, which are the field corrector and the field flattener. And this is the filter right in front of the last, the Dura window, which is curved as well, and then here are the CCDs. And what you see is that this filter on axis sees the beam in a nice symmetric cone, but when you go to the edge of the field, this cone enters at an angle. And so in an interference filter, that translates into shifting of the waveband. And you can model all this and you can measure all this. And here's an example of the R-band filter, for example. This is the filter throughput, a nice flat throughput over the R-band range. But this is the central wavelength as a function of distance from the center of the optical axis. So you go out to 15 centimeters in the corners of this field. And so you see that gives you a shift of about 8 nanometers, 80 angstroms. So that's not much on the waveband of almost of 1,000 angstroms, but nonetheless, it's important if you're trying to get to 1% photometric accuracies, photometric redshift accuracies. And this is the same curve for the red and the blue wing of the filter, the red and blue edge of the filter band pass. So things like this you simply cannot ignore. All these things enter at the 1% level easily, and You can think about how you model them, but you have to think about them.